Hi, this is Will, and I wanted to show you this one thing I've been playing around with. For the Siemens S7-1200s and all their models, they have these technology objects, and they're pretty neat. And of course it's in the wrong spot, but if you look at this technology object, there's two of them. One is called counting, and they have these counters, and then there's one called PID Control, and they have, let me see if I can move this out of the way. But anyway, what we have is a little DC motor that we're controlling, and basically it's a pretty simple program. We've got some start-stop logic, and we've got an enable in there. But they have these just these counter timers, and this one is the control high-speed counter, and I guess it's external. And if we looked at the data sheet on it, they've got these two things with the extended is what it means. They've got two parameters. One is elapsed time and one's edge count. And it's, you know, the time between rising edges of edge count. And then there's the number of rising edges within an elapsed time. And what you can do with it is they've also got this program here where they do calculated speeds, and this is just a program I found at Siemens. And you know what you do is, if you have the edge count and the elapsed time, if they're both valid, you can calculate the period. So there's just this SCL program that someone has written from Siemens, because it's looks like it's Siemens AG that wrote it. So these are some programs that you can get online if you know how to look for them. And of course I just tripped into it by accident. But you know, if you know, and I guess three things you need. You need the elapsed time, you need, you know, the edge count, and you also need to know the number of pulses per rotation. And, you know, a lot of times, and the way this program was originally set up was for an encoder. And an encoder is going to have a number of pulses per revolution. Now, we didn't have an encoder, so what we did is we just kind of, and I'll show it in a minute, but we just kind of put together something to be able to count. So that's one of the things that we have. So this just generates the speed. You know, it gives us what the speed is. And so it's running at, you know, 650 RPM right now. And there's also a second, and what you have to do for the PID control is you have to set up a cyclic interrupt that just interrupts the main program occasionally. And I think, well, if we get into the cyclic interrupt, come on. Okay, so the cyclic interrupt, what we do is we just normalize some of the results, and then this one is, it's kind of like just a percentage of a scale, and so it's running about 26% of well, what we have here is full speed, which is 2500, which is a ridiculous high number. And then there's this PID control. And so here we have the set point that we set on the HMI, and then the input, which is the speed in, which again comes from the other block that calculates the speed. And right here, this is an analog output. Now that analog output is based on, you know, the analog number that Siemens uses, which for their purposes, the analogs go from 0 to, I believe it's 27,486, which turns out to be about 20%. And these are just some, errors we've got to reset in there because the thing does glitch up every once in a while, so we have to reset it. And here's where we can, we can take that voltage, and the ratio of 535 to 27,648 turns out to be 1.9 volts. And so this 1.9 volts, what we have this going to is we just have this going to, and I'll show it here in a second. We've got a regular 1200 PLC, but we've also got some analog outputs. So we can take an analog output, 0 to 10 volts, and run that through a circuit and an op amp, and we can get the motor to run at the proper speed. And let me just show the webcam here, and you can see that it is 650 versus 651 now, and here is the analog voltage output, which you can't read because it's too small, but right now it's at that 1.92 volts, so that's at the 20%. And for the screen, what we have is we've just got a main screen that starts, stops, and resets it, and then we have speed control, and sometimes it actually works. So what you can do here, and the motor only runs up to about 1200 RPM, or maybe a little more than 1000. But if I go in here and I can change it to, let's say, 900, and then I have to hit the arrow, and what happens is it starts jumping up. Now it gets up there pretty fast. It does overshoot it pretty good amount. You can try to optimize the PID loop, and that takes a little work. One of the tools that they have in here, and I'm going to have to minimize the screen here, but if you go into this PID control, and it's called the Compact PID Control, they've got two things. One is configuration, and the other is the commissioning window. And so if you go in here, with this, you can put in the controller type. It's a speed controller. They have a whole bunch. If you want, voltage, power, temperature, all these other things that, I don't know how those would work. I mean, I guess I know how temperature and pressure would work. But, we have speed. We're going to say it's going to be in RPMs. We've got input and output parameters. So our input, we're getting the input directly from the calculated block. This output, PER, means per the analog outputs, which again for Siemens is a 0 to 27,468. So you can also set up the input like that in case you have the speed input coming through an A to D converter. We don't have that. And then there's some processing sections, and again, we have these set ridiculously high. These should be probably about 1200 maybe. But you just set the limits, and then here is where you say, okay, for the process values, now it's disabled, but again, for 0 to 10 volts will be scaled inside the PLC from 0 to 27,648. And then we have some advanced settings. Again, we have the really high ones. Now, you can also use pulse width modulation. What I found is the motor's so small that when we hit it with the pulse, it just goes back and forth, back and forth. So that's for pulse width modulations, and that's what that is. And again, the output was way too high. The output values 0 to 100%, and the PID parameters. Now these are what's inside the PID control loop, and again we just use P and I don't see any need for using a differential or a derivative function. But what we have, and I'm going to change, like right now we're at about 900. Now, a couple things, and I'm going to show you the motor setup we have, but we can only make it speed up. If we're taking that 900 down to, and I'll take it down to like 400, I'll take it down to 500. You know, it can only turn off all its voltage and then slow down by itself. And what you can do, so this is the configuration, but if we go into the commissioning, you get this type of screen. And right now our screen is kind of set up, except, so we've got the set point, the scaled input, and the output. And we should probably change this because this is on the 2500 scale again. And let's see, one of these, maybe this one, vertical zoom. Oh, nope. What we want is we want this table. And because, you know, we've kind of said we're only going to run it to about 1,000, I'll make the scale 1,000, and then it'll actually you know, have better resolution. Okay, so now we're just looking from 0 to 500. And now if I get this guy out of the way, we can take a look. Now I'm going to change this to 500. You're going to have to trust me on this. And when we change that, what I'm going to do, well, I can do it right now, is I'm going to start this. And we'll have 500 in here for the set point, and it'll be 900 because that's what we have right now. So I can start this. And you can see how immediately the set point drops. And you can see how the PID loop kind of hones in pretty quick. Now this one isn't tuned. I've had one that I was playing with that's tuned pretty good, but you know, within 10 seconds or so, it you know, gets to speed, and you can see it's at 499 versus 500. And you know, this is a pretty good thing for if you just want to see what the circuits look like and how they function, and if you really wanted to tune them really good. You know, this does have a function with pre-tuning and then fine-tuning. Now I've found that the pre-tuning is pretty good, but the fine-tuning, I got some problems with that. But so that's what it looks like. And I'll go back up, and this time I'll go back up to 1,000. Now again, it can only slow down by, you know, virtue of its inertia and windage being in the motor. But if I put it up to 1,000, and what you're going to see it happen is the set point goes up, but the set point line jumps up really fast. So that's up to 1,000. And here you can see it's trying to lock in, Now, it locks in a little better because it is able to control the torque parameters. Now, it's still quite high. It's at 25. And I think that's kind of the limit of how high it'll go. We can try that again. I think I'll go back down to 500. And then maybe only take it up to like 950 and see what the curve looks like if we don't go up quite as high. So you can see when it slows down, it does overshoot, and then it turns the motor back on and it tries to get in there and lock. And you know, it locks in fairly quickly. I mean, it could be better, I'm sure. So let's go back up to, I don't know, I'm going to put it at 925. And we can see what it looks like on the up ramp. And here you can see it's step climbing, step climbing, step climbing. And it's got its overshoot, but then it should come down. And hopefully it will come down in fairly good fashion. And that looks alright. Now, you know, it does have this pre-tuning mode, and what it does for that is, because it doesn't know, if it's an original thing, it doesn't really know what type of motor you have, so it gives it really high pulses at first, and then as it's figuring out the mass of your motor, it starts zeroing in on, you know, what the parameters should be. So that's a pretty neat program that I've kind of been playing with, and you know, it works on this you know, these technology objects, but one of them is the PID Compact, and the other is the high-speed counter. And you can find a lot of data from Siemens' website for both of these. Now, you know, what we have over here for what are we trying to control. So we've got this, and this is a screen that just says we're at 520 or 925, which we should. You know, here's, and I'll have to move this around. You know, here's my Siemens controller. This is the COM unit. This is the 1200, and this is analog output. Now, as far as our motor, and let me see if I can get in here tight. You know, we've just got a small motor, and we take the analog voltage that's output from the UPS and we just run it through a voltage follower, and then it runs through an op amp. And I think it's a TIP 120 op amp. Now, over here, for our motor, which is kind of small, you know, we've got a load weight on it, which helps it. And then we've got a 3D disc that what it's got little magnets in it, and then it's got a Hall effect sensor. So every time, and maybe let me turn this off. So every time the magnet passes the Hall effect sensor, it gives a pulse. Now, once upon a time when I was using the actual you know, the actual screen for come on, I guess it won't let me do that. And one of the best ways I like just to stop it here. Seems to be a little more reliable on stopping it. And so what we've got is we've got 4 magnets here. Better enlarge my screen. So we've got 4 magnets, and every time the magnet passes the sensor, you can see the pulse. Now, we've got 4 magnets rather than 1 magnet because once upon a time when we were playing around with the pulse width modulation, and it was really unsteady, so we thought maybe we could get better control if we had more pulses. But, you know, it's a nice little motor, and there's actually another program that I wanted to fool around with that's a really nice program for the HMI that is a Siemens program. It's totally Siemens. And again, this just has the last values because oh, our system's off, so it's not going to register. But that's basically a pretty neat little program that I've been working with. the Hall effect sensors are neat little devices if you've never played with them. So anyway, that's the little program on the PID control and analog output for the S7-1200.